In this video, we're going to talk about the octet rule and how we can use it along with valence electrons from the previous video to determine what types of ions will be formed. So first is simply stating the octet rule and understanding the basis for the rule, and then using it to, again, figure out what ions are going to form. So our octet rule, if you know what an octet is, it means 8. So this octet rule means that all atoms are going to want to fill their outer shell and for most atoms, or all of our representative atoms, and if you don't remember what a representative atom is, go back and review chapter 3, but all of the representative atoms, a full outer shell means 8 electrons in that outer shell, with the exception of hydrogen and helium. For these guys, the outer shell is 1s, so a full octet for hydrogen and helium is 2 electrons. Everything else that's a representative atom, a full octet is 8 electrons in that outer shell. So knowing that all atoms want to achieve a full octet, this then helps us figure out what ions these elements are going to form. So to form ions, you are either gaining or losing electrons. And the whole purpose behind gaining and losing the electrons is to achieve that full octet. And the atoms are going to do it in the simplest way possible, meaning if it's easier to gain 2 electrons than to lose 6, it's going to gain 2. And it really is all about the numbers. So if gaining is fewer electrons than losing, or if losing is fewer electrons than gaining, that's how you decide which direction it's going to go. So let's look at a couple examples here. So the ion formed when a potassium atom loses 1 electron. So if we look at potassium, potassium is number 19. It is in group 1. So the potassium atom has 1 valence electron. So that means it has 1 electron in its outer shell. So it can either gain 7 to fill that outer shell, or it could lose the 1 that's currently in the outer shell, and then the next shell in becomes the outer shell and it is already full. So sometimes this is easier to do by thinking about the electron configuration. So if I write out the electron configuration for the potassium atom, you can see that I can either get rid of this 4s1 electron, and then the new outer shell becomes the shell 3, and it already is full with 8 electrons. Or I could go in and change this to 4s2, add in the 4p6, and now the 4th shell is full, but that's working with a lot more electrons than simply losing the 1. So that's not going to happen. So potassium loses that 1 valence electron. The new outer shell is 3 and it's full. So if I get rid of this 1 electron, potassium, and the way we're going to write these ions is it's got a positive charge. So what was the outer shell is now empty, and we take away that 1 electron. And if I remove an electron from something that's neutral, I end up with a positive charge. So this is what our symbol is going to look like for potassium ion. It's also, in general, not wrong to write K+. We'll see later where the brackets are more important when we're really actually drawing the Lewis structures for these, but K+ in this case is a sufficient answer. Part B says the ion formed when a sulfur atom gains 2 electrons. So if we look at sulfur, sulfur is over in group 6. So that means it has 6 valence electrons. We can go through the electron configuration if you wanted to. Another way we can do this is we can see, well, if I'm looking at these valence electrons, I could either get rid of all 6 that are there, or I could add in 2, and now I have 8, and it's a full outer shell that way. So adding 2 is easier than losing 6. So the ion that is formed, if I add 2 electrons, remember electrons are negative things, I'm going to end up with a -2 charge. Another example, we're going to fill out this table, kind of think about how different things are related. So A says we have the chemical symbol of Be, which is beryllium. It tells us that we have 2 electrons. Number of protons we know by looking at the atomic number on the periodic table. Remember, protons cannot change. We're only forming atoms and ions and charge by changing electron counts. So beryllium is, again, number 4 on the periodic table. So that means it has 4 protons. If it only has 2 electrons, that means it's going to have a +2 charge for the ion. The Lewis symbol of the ion. So first, if we want to think Lewis symbol for the neutral atom, 2 valence electrons, but I've lost those 2 valence electrons, so what's left is none, and then that as a whole has a +2 charge. So again, positive ions are going to be the element symbol with no electrons around it, brackets, and then your charge on the outside. Row B tells us number of electrons is 54. It tells us the number of protons is 53, and protons tells us what element we're looking for. So if we find number 53 on the periodic table, it is iodine. So that's our chemical symbol. Ion, we've got 54 electrons, only 53 protons, so that's 1 more electron, so it's a negative charge. Negative ions will always have all 8 electrons in the outer shell. Again, that's why it only adds 1 electron and not 2, because it only needs 1 to fill that outer shell. So again, we'll use brackets, and then the charge on the outside of -1. At this point, maybe we're noticing a trend, maybe not, but I'm going to go ahead and point out a trend that we have here. The group numbers and charge, there's a pattern. So group 1 has 1 valence electron, and it will always lose that 1 valence electron to form a +1 charge. Group 2 has 2 valence electrons, so it will always lose those 2 and form a +2 charge. We're going to ignore the transition metals for now because they don't have a set trend. We'll talk more about those in a little while. I'm going to jump over to group 3, and again we're looking at the Roman numeral numbers. So group 3 over here, it's easier to lose 3 than it is to gain 5, so that means +3 charge. Next one over, we have group 4, which is 4 valence electrons. So to get to 8 from 4, we can either lose 4 or gain 4, and technically it could do either, but usually it does neither. Right? Group 4 typically doesn't form ions. Next group we have is group 5. Now we can either lose 5 or gain 3, and it's easier to gain 3 electrons. So being negative, that gives it a -3 charge. Group 6 has 6 valence, so to get from 6 to 8, it's easier to add 2 electrons, so that's a -2 charge. And then group 7, it's easier to add the 1 electron, so that's a -1 charge. And then last we have group 8. Group 8 already has a full octet, so it also does not form ions because it's already satisfied the way it is. It doesn't need to add or lose any electrons. So now, keeping this in mind, let's think about practice question 5 here. Part A says write the ions produced by calcium and bromine. So now that I know this pattern with group number, I can just see what group these atoms are in and determine what the charge on the ion will be. So calcium is in group 2. So group 2 always forms a +2 charge, so the calcium ion will be +2. Bromine is over here in group 7. Group 7 always gains 1 electron and has a -1 charge. So B, we've kind of already answered how many electrons are gained or lost by each. Calcium, we are losing 2 electrons. And bromine, we are gaining 1 electron. C wants us to write the electron configuration for each ion. So for calcium, calcium is in period 4. It's in the S block, and it's the second one over. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's calcium neutral. We said calcium loses 2 electrons, so we are going to get rid of the 2 outer electrons, and what we are left with is all the way up through 3p4. And remember, one of the shortcut ways of writing these electron configurations is to go back to the previous noble gas, which in this case would be argon. And this is argon's electron configuration, all the way up through 2p6. I'm sorry, this is my mistake. This should have been 2p6 from the beginning. So, calcium ion, if we lose those 2 outer electrons, it's going to revert to what the electron configuration for the previous noble gas is, which is argon. So that's going to be true for all of these ions. It's either going to go to the previous noble gas if it's losing electrons, or it's going to go ahead to the next noble gas if it's gaining. So if we look at bromine, bromine is down here in period 4 as well. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. So we're adding 1 electron. So what was 5 electrons in that p orbital, or p suborbital, is now going to be 6, so that we fill. The 4p6 corresponds to krypton, so we could also write this electron configuration as Kr.